Hello! Those of you who are regular viewers of the channel are probably aware that I do not do intros to my videos and I've never done one before. If you weren't aware of that, you can go back through my videos and realize that I don't do intros, but anyway, I just wanted to actually put my face in the video because for those of you who like when I go to the desk, this is going to be a very desk-oriented video because there's going to be diagrams and trees and things that maybe will stop people from Reddit saying that my videos are unbearably boring for once. So without further ado, let's go to the desk and talk about stars. Hello and welcome to my very professional setup. So like I said, I need to do a lot of drawing for this because it makes most sense to like see this physically as a chart, at least to me. I'm sure somebody will be able to argue with me that there's a better way of doing it, but I don't care, this is how I'm doing it. So we start off with a nebula. The thing you might notice about nebulae is that they're not stars. But you know, eggs aren't chickens, so whatever. This can be either an emission nebula, which is probably what you imagine when you imagine a nebula, not a nebula. So here's a lovely picture of the Orion Nebula. That's what you're imagining typically. They can be born there. However, they can also be born horrifyingly in dark nebulae or absorption nebulae, but I already wrote the word dark. In which case they may very well be the only visible light source in their immediate area. So a nebula is basically a cloud. Nebula literally means cloud in Latin. Big collection of dust. And over time this dust will move around as dust does. I'm sure you've seen dust at some point in your life. And it will clump together and it gets bigger and bigger and bigger clumps until eventually you get something that looks like this picture that is now on the screen, and that is a protostar. A protostar is not quite yet a star, hence the name. They have disks of matter just floating around them, sort of similar to the disks you see on a planet. If you know anything about the disks around planets, you know that they can, on occasion, become moons, and this is the same instance with the disks around protostars. They eventually become planets or they fall into the star, and once enough matter starts to fall into the star, it can go one of two ways, and this depends on how much mass the protostar builds up. Then we get a brown dwarf. I have a whole video on these, and they're basically failed stars. So they are visible, they do emit light, but they do not fuse hydrogen like a typical star. And this is the end for them. They don't go any further than this. They just burn through whatever fuel they have and get dimmer and dimmer until we can't see them anymore. Less than. There we go. That might be helpful in understanding what's going on. But if it's greater than, and I'm not going to write that again, then we get a main sequence star. This is the kind of star that the sun is, so you should be familiar with what one looks like. And these stars constitute about 90% of all stars in the universe, as far as we know. A star is made up of a core with a shell around it, and typically the shell doesn't actually fuse anything, it just sort of sits around the core. and the core is kind of crunched in by the shell, and the force of the gravity from the shell on the core generates heat, and there's a direct relationship between how heavy that star is then and how hot the core is. And the minimum temperature to fuse hydrogen is about 10 million degrees Celsius, and so this 80 Jupiter masses is more or less the minimum to get hydrogen to 10 million degrees Celsius so it can fuse. And once again, mass is very important in how long a star will actually spend as a main sequence star. So the sun will spend about 10 billion years as a main sequence star, and that's in comparison to about 100,000 years as a protostar. By the way, I forgot to mention that. But compared to that 10 billion, a star with 10 times the mass of the sun would only spend 20 million years as a main sequence star. And then a red dwarf, which is closer to this 80 Jupiter masses, so the smallest main sequence stars, are estimated to be able to spend about 12 trillion years as a main sequence star. So mass is incredibly important to how long that will take, and that's largely to do with the temperature. A bigger star will have a higher temperature, so it will fuse things much faster. And the other thing that the size is really important for is moving on from the next sequence of a main, next step from a main sequence star. So, again, going down to the smallest, and we're going to draw it like this. You'll find out why later. We have our red dwarfs, which are smaller than about 0.6 solar masses. That's the symbol for a solar mass. So these become white dwarfs, and this happens kind of slowly over time for a red dwarf, so it just starts to get to the point where it's sort of running out of hydrogen, and then it will just gradually cool down and become one of these guys. These guys become red giants. So what happens here is, instead of gradually cooling down, because these guys are at a much higher temperature, they just sort of suddenly get to the point where there isn't enough hydrogen for significant hydrogen fusion to happen anymore, and so it just sort of stops. Once there is not enough heat coming out from the core, well, the heat is what causes pressure in here. So if you think about when you're cooking, if you put the lid on a pot, that causes the temperature to raise up, and then you get steam building up inside of it, and it starts to eventually push on the lid and bubble up and stuff like that. And the same thing happens with a star when the core is hot enough. It pushes the outside outwards. But once it stops doing that, then everything collapses back in again. And then this has a reversing effect where that pressure will cause the core to heat up again. And for a star that is large enough, it will then, which is this 0.6 solar masses, it will then produce enough heat to start fusing together helium instead of hydrogen. And helium outputs a lot more radiation than hydrogen does when it fuses together. So then the star swells up much larger and becomes a giant star, and at the same time, being a giant star, its surface area is much larger because the star is larger. so the outside is cooler, which gives it a red appearance. Okay, camera has not died yet. And then these 0.6 to 8 solar masses go here again. Because at this range, once they fused all their helium, that's really it for them. They don't have anything more they can do. So they end up in the same boat as the red dwarfs, where they've run out of all the fuel that they can use. So they're just kind of sitting ducks at that point. And a white dwarf will glow white because stars are, and this may be surprising to some of you, hot. And at this point they are still hot, but they are no longer producing heat. So this is the difference between, say, well, I guess we'll go back to the cooking analogy. Having a pot full of boiling water with the heat on underneath it versus turning it off. This is a pot that doesn't have the heat on anymore. So it's just going to get cooler and cooler and cooler, and I don't want to draw on the next page yet, so I'll just do it here. These guys eventually become black dwarfs. So a black dwarf is just a star that has run out of its fuel and it has cooled down to the point that it is the same temperature as the cosmic microwave background. So basically it has cooled down so much that it physically cannot cool down anymore. But going all the way back up our tree, we're still not done with our main sequence stars yet. So the same thing initially happens. Really good at remembering that too. Okay, so initially they become a red giant and they do the same thing. They run out of hydrogen, collapse in, start to burn helium, spread out again. Okay, my flatmate has stopped gracing us with her background noises so I can start talking again. Okay, so it does the whole helium thing, and then again it collapses in, just like the smaller stars do. But then at this point, we'll make that the correct number. Okay, at this point, they actually have enough heat to start fusing together carbon. So the cycle repeats itself. It shrinks in, it heats up the core, it expands out again, and then it does the same thing, keeps burning until it runs out of carbon. But, oh, look how many pieces of paper I have. Lo and behold, at this point, it does not become a white dwarf. It goes off and does something different. So our first option, and we can pretend this is one long piece of paper, is less than 29 solar masses. And at this point we get a neutron star. And neutron stars are very, 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 very dense. They're some of the smallest stars. You can imagine, you know, nearly 29 solar masses getting shrunk down to like 10 to 20 kilometers across. A teaspoon's worth of the mass in a neutron star would weigh about 1 billion tons, and I believe that is imperial tons, not metric. And now you'll notice that we're only left with one more option to move forward with, and You've probably guessed what it is at this point. Leaving anticipation for those of you who haven't. That's right, it's black holes, and I misspelt it again. So a black hole undergoes a similar process to a neutron star, but because of their huge masses, they collapse to a point that even light cannot escape them. And you can actually kind of see this coming with neutron stars, even because something has to travel at least half the speed of light to be able to escape a neutron star. So it's kind of just taking that next step up, really. But these guys are obviously very famous for more or less tearing a hole in space. And it's more than just that light can't escape these guys. We can't even model what would happen inside of them from a mathematical point of view, and this is often wrongly attributed to Albert Einstein. He did come up with the theory of special relativity, which you need to figure this out, but it was actually Carl Schwarzschild who did the mathematics and was the one who kind of accidentally theoretically proved that black holes had to exist if you concentrated mass into a small enough area. And that's kind of all the big steps that there are for how stars work. There's more than this, as you might guess. There's a little bit of leeway anywhere you have between 80 Jupiter masses as a cutoff. It's not like 80 Jupiter masses and 1 gram more and bam, it's a main sequence star. So there is this diagram called the Hertzsprung-Russell diagram, but that is another way of visualizing the life cycle of a star in a less kind of linear way. I hope you enjoyed this video. If you liked this video, I have multiple other videos on stars that you could also watch. I always include sources in the description if you'd like to read more. This is definitely a topic for which there is more room for reading. And if you have any questions or any comments, anything you want to say to me, you can leave them in the comments below. I'm sure you have used YouTube before.